introduce again Danielle. Welcome to our seminar. We're happy to have you. I think that this work will build on work that Matt Insall talked to us about 6 months ago, maybe, regarding the extension monad. And Danielle will build on that work based on work that she did for her thesis. So without further ado, go ahead, Danielle.
Okay. Yep. As he said, I'm going to be talking about extension monads and a couple of structure theorems related to their expression and their utility. And as he mentioned, this does follow Dr. Insall's presentation from February. And we'll be taking his basis of nonstandard methods and universal algebra and combining them using the extension monads to learn new information. So first, we take a set, often denoted as U, sometimes with a tail. I tend to not tail my U's, that contains specifically atoms, which we don't want to have any structure whatsoever. They are not sets. They are not classes. They are just given as elements or potential elements. And we want to construct what we call a superstructure that will contain every typical structure on this set of entities and its power set and the power set of that, etc. Often denoted as V of U, which will just be, in effect, U union the power set of U union, and this is a limit object, so it's impossible to write in sequence like this, but you take the power set of all the previous unioned members. So this whole infinite union, it's only a countable union for our purposes. We don't need to create a whole new language or anything. But it has every possible algebra, topology, relational structure, and more on the various elements of our U, and on the sets of U, and on the sets of U, etc. And since superstructures carry so much structural information, it can be very advantageous, but also very difficult to find other superstructures that allow for any sort of morphic embedding or structural mappings. But Wash did show that for two superstructures, one of which is formed out of a set U, and the other of which is formed out of a bigger set, star U, that there does exist a construction of a star mapping in such a way that we can fully embed this superstructure into this larger superstructure without just having some sort of boring identity. This is done using special orderings that we call filters, and then using those special orderings to define equivalence classes on membership to create this new notion of membership. And as demonstrated by Wash and I believe Mostowski, we don't need to worry about the difference between this new notion of membership and actual membership.
Danielle, quick question here.
Yes.
Is there an implicit uniqueness to the star operation?
No. I don't believe there is only one star operation that works.
Okay.
You could construct a whole bunch of different special orderings as long as they follow certain properties that require being cofinite or ultrafilters that contain every cofinite set of some indexing set.
Mm, mm, mm. Cofinite
Some
meaning that you're
infinite,
only leaving
yeah,
out a finite number.
only leaving out a finite number.
Right.
And
And
you
so
can
you're
see the archive paper for more technical details on that, but it does get into pretty specific minutia. So
no, absolutely. And I'm glad that we're not going there, but I just to understand it in words. So you're extending first a set of atoms, then
yes.
and we are also extending with this outside star the superstructure on this extended set of atoms, right?
Mm-hmm.
So
Mm-hmm.
this object on the right isn't the standard superstructure, it's some extension of it. And the whole point of this theorem is that you can embed the original traditional superstructure on the traditional set of atoms inside this
Mm-hmm.
extended superstructure on the extended set of atoms,
Yes.
such that you maintain a nice mapping, that this mapping has
Yes,
this
yes.
embedding is a proper embedding. Okay, okay.
And this image that we have here is only part of like the true superstructure on the star view. Since we have a smaller structure on the left, you're not going to be able to cover everything on the right.
Naturally. Yeah.
And that
Yeah,
allows
so
us to have some differentiation between different types of elements that we'll get to later. Okay.
so just a small point. Do you mean V of star U or do you mean star V of star U?
We often denote it as star V of star U
Okay.
because specifically this is going to be the image of, well, not the image, but it's going to be related to the image of V of U under this star. I guess you could, in the sense of ordering superstructures or superstructure-like structures, you could say that this is within the just standard superstructure of star U. Okay.
Oh, good. So that's what I was interested in, that relationship. I'm glad, Irfan, you asked that question. So this outer star, which is kind of specifying the superstructure, isn't necessarily an extension, or is it some sort of further specification of it? Or maybe it'll come up in the rest of the talk in the examples you show us or something.
Hmm. We tend to not be quite, for the rest of this, we're not going to be nearly as zoomed out to the full superstructure, so
Okay.
it won't necessarily come up as much later, but yeah. It
Yorgos has a
often,
question. Sorry, go ahead. Complete your thought. I'm sorry.
oh, sorry. It often, how do I put this? I think the preferred way of writing this whole thing is with the star due to, I believe, what I've said.
So
But this is one of those things that, yes, did you have a question?
Yes, a very quick question, and it may have a negative answer. That would be perfectly fine. Is there kind of a standard or a canonical example, to put it in concrete terms, starting, say, with the natural numbers or something simple, that, let's say, the superstructure, the V of U, would
Oh,
be
the V of the
something?
natural numbers? I mean,
Yes, yes, yeah.
so that would be, and if we're looking at just the set n, I mean, you're going to get this collection that includes every natural number, starting with 0 for our purposes, then every set. Oh, wait, sorry. So then you have to write out every subset of the natural numbers, which gets pretty large. And then you get sets that both contain other sets. So yes, you can give example members, but writing the whole thing out is not very feasible.
Thank you. Thank you.
So I have a quick comment to continue on the previous question. So
Mhm.
usually I have only seen V of star U in usual places where non-standard analysis is described, but I can see star V of star U also being a thing if you consider, for instance, iterated non-standard extensions, because
Mhm.
what is happening is usually when we do one non-standard extension, we are specifying a standard universe, and then for every object in the standard universe, there is a star of that object.
Mhm.
But the star of that, so for every object in V of U, the star of that object actually does live in V of star U.
Yep,
But
that's
if you
true.
think of V of U itself as a set that is contained in a universe as an element that you are extending, then there will be a star V of star U, which will have a
Mhm.
slightly different, maybe nuanced meaning. But for most practical purposes, for when we are considering one single non-standard extension, I think saying V of star U is usually enough, and that's what people often say.
Mhm. That's fair.
Just to be also extra clear and building on your answer to Yorgos's question, I mean, this, for example, will clearly contain all the real numbers, which are just members of the power set of n, essentially.
Mhm.
Also, a lot more of things that are multi-type objects, essentially, like you were just saying at the end. So it is literally considered, this would be, that's why we call them the hyper-real numbers, for example, right? Like, I mean, to
Mhm.
make that connection, but it's a more
Yeah.
general.
But that's given the stars. This is just the standard superstructure, so that will come up a little later. Any other questions? Okay. So this is just a simple diagram for this whole V of star U. And we have this embedding. This is sort of the star embedding here. You get not only the image, but you get things inside of imaged elements that form this internal portion. And this is really what we want to look at, but there are a few other terms that we'll talk about on the next slide. But as you can see, it's just a countably infinite sequence of concentric, effectively circles here, but power sets in the actual case.
Just for clarity, sorry, could you bring that back for a moment?
Yes.
So
Mhm. Oh, sorry.
the outer circle on the left, V of U, is the object we've been talking about.
Yes, this
The
whole
inner ones, do you, like when you say V1, do you mean like with the first level of the,
iteration,
just
yes.
the power, you know, the union of U and the power set of U or something like that?
Yes, yes.
Okay, and then V2 is the power set of, you know, that union, the power set of that. And so on. Okay, understood.
That's the technical method of how we define it. We use V of U equals the union I equals 1 or 0 to infinity of V sub I of U, defined as you just said, yeah. Okay. So there are three main kinds of elements. We mentioned internal here, but an element is considered specifically standard in the non-standard superstructure if it is equal to, in effect, equal to some element of our original superstructure. It's internal if it's either the direct star mapping, so it's like star of some A, or it's an element of some star of A, and etc. And everything else is considered
What do you mean by
external.
equivalent here?
Sorry,
Do you
equivalent?
by yeah?
It depends on how you define your atoms and your other elements. Excuse me. In our case, we're going to treat star of some atom is equal to the atom itself, but since it's an embedding, you can define an equivalent mapping such that this is not true in like an outside of context sense. Does that make sense?
Yeah, and just to be clear, when you say atom, you mean an element of U to begin with. And
Yes.
fundamental single element, so no subset.
Fundamental elements,
Thing
yes.
itself. Yeah, okay, good.
Mm-hmm. Once you get past the atoms, the set structures become a lot more understandably equal or non-equal. Excuse me.
So that this is really the distinction between standard and internal, essentially, is that, right? Because
Mm-hmm.
clearly the
Well,
standard ones could be
standard
formed-
elements will be internal as well.
Exactly. That's
Yeah,
my point.
so-
Yeah.
Mhm.
So in some places,
Oh, standard.
people say that
Okay, sorry, that's not true.
in
Some
some places
standard
people say
elements are
star
internal.
of.
Sorry, keep
Sorry.
going.
I'm still just a bit confused. Some places people would say star of something itself can they consider it to be standard, but the convention can vary from places to places. So do you mean that star of an element, that object itself is also going to be called standard, or no?
No,
So
not
if
here.
if I look at, okay.
Nope,
So
I apologize if that is
standard
confusing.
should mean, so standard should mean it is uh it must be some, I guess it must be some atom in the standard universe whose star we are identifying with itself, or it could be a finite set of those atoms, I guess, because any infinite set, if you take star, you will get something bigger.
That is
Is that right or
true
no?
when you take the star of an infinite set. So, for example, the star of the natural numbers is not going to be the same as the natural numbers. However, as we've talked about, the whole superstructure is not only elements that are related to or mapped directly to elements from the smaller superstructure. So if you look at the natural numbers, you've got something like this: 0, 1, 2, 3, 4, etc. You know, the typical. I tend to prefer including 0 in my natural numbers because I like having a name for all of the positive integers plus 0. Whereas when you've got the star of the natural numbers, since you have a lower bound, 0 still remains the lower bound. But without an upper bound, you end up getting things that are much larger than any standard natural number. Often we refer to them using Greek letters such as mu. And you've got what is in effect here, sorry, mu plus 1, mu minus 1, mu plus 2, mu minus 2. You've effectively got another copy of the whole integer line at this point, and you can do the same for 2 mu or mu divided by 2 or other internal hyperfinite numbers. However, you get a lot more elements. And while there does exist a copy of this in the whole superstructure of star U, because this just refers to all elements of the power sets, right? So if you have all of these atoms, you're going to have this inside of here. It is standard, but external. Whereas star n, because it's being directly mapped to, is going to be internal. but not standard in our case. Does that make sense? So for a lot of what we deal with, as you kind of alluded to with your question, we treat external elements as if they don't exist for a lot of our purposes, but they do technically exist in the same superstructure, which does allow for some comparisons, just not as much with like the transfer principle. Okay? Any questions?
No, thank you. Thank you for the clarifications. I think it will become even clearer moving forward, but yes.
So this is the most fundamental utility of superstructure enlargements. It's the transfer principle, which allows us to take logical sentences relating to elements from the smaller superstructure and move them over to our larger superstructure by starring everything that is not a quantified variable. So for example, a sentence like, for all elements x in set big X, we have that for the function f from big X to big X, f of x equals f of x. And you see that when you've transferred it, you get for all elements little x in set star of big X, we have that for the function star of f, from star of big X to star of big X, star of f of x equals star of f of x. So like I said, everything that's not a quantified variable is going to have a star applied to it to allow for the transfer to occur. And the truth of this first sentence is dependent entirely on the truth of this second sentence and vice versa. So it's an if and only if relationship here.
And this hinges on the fact that there's the x itself is embedded inside star x, so that this, in other words, is a in some sense smaller statement as far as the star x construction.
Yeah, but that's what's interesting, is that we can start with a smaller statement and still, if it's true, we've proven a larger statement, or vice versa. That's what's so handy. Because of the way that we have defined our star mapping to allow for everything in here to imitate stuff in here.
Is it accurate to, is it not incorrect to extrapolate the example which you gave before about the embedding of n in star n, in the copies, in the hyperfields, and to say, for example, we could have had some natural number, function f, some statement, some algebraic identity, let's say, which we started off with, and then that the extension essentially is saying that the same thing would hold in this more general setting.
Oh, of course, yeah. For example, let's
copy of the in the first copy, and then the new copy in the is that something?
Yeah, I mean, you could, for example, in the nonstandard natural numbers, you've got infinitely large prime numbers because there are arbitrarily large finite prime numbers. So you could define a sentence that describes the prime numbers and then transfer it to get that there's always a larger prime number, even in the nonstandard setting. So something of that sort. So all of nonstandard methods in this way is a conservative extension, meaning that it's not going to prove anything that couldn't be proven in the original nonstandard setting. It's just often a useful tool, and it can often speed up proofs. I believe it's been shown that there exist proofs that would take longer to prove using standard methods than our sun has left in its lifetime, but that could theoretically be written down in a person's lifetime using non-standard methods, but I haven't verified that one for myself. Any questions so far?
I wonder, it's not a question, but I wonder, my mind, when you just said this, and I'm not sure if you know the answer to this, it's just kind of speculation here, but my mind went to these peculiar statements, kind of like the Goodstein sequence properties, or, or other kind of, maybe Collat's conjecture type things or whatever, like numerical statements that appear to rely or to be sort of possibly unprovable in the standard setting, or to get to some result of this kind. This is where my mind goes. It might be wrong, and I'm not sure if you know enough about
I have
it.
not looked into that, so.
Okay. It's a curious thing for me. Anyway, thank you.
Anything that's referred to by some mathematician's name is something I'm going to be much less likely to know off the top of my head. Sorry. Not good with names. Are there any other questions or comments, I guess? Okay. So related to our discussion of the transfer of the natural numbers and other transfers, the transfer of any individual finite set of atoms, as you said, Irfan, will be the same set, given that we have the same atoms in both underlying sets. However, finite sets of non-atoms, due to the fact that the non-atoms themselves may change, will not necessarily be the exact same set. So for example, the set containing the set of the natural numbers is not equal to star of that set. Even though this is technically a finite set. It's still going to have the same cardinality, but it will be the set that has the set of non-standard natural numbers in it. And of course, as we've discussed, you end up with larger than finite numbers when you transfer the natural numbers themselves. The same thing is true when you transfer the collection of finite sets of some set. This star of the finite subsets of A will get you more than just the finite subsets of A, assuming the cardinality of A is infinite. And the cardinalities, because they're not in the original finite subsets of A, you're going to get that they're potentially arbitrarily infinitely large cardinalities. Hyperfiniteness here just means that in the context of internal sets only, they behave like finite sets. So they're well-ordered. Any internal set contained in a hyperfinite set will also be hyperfinite. Hyperfinite unions of hyperfinite sets will be hyperfinite, etc. By the transfer principle, you can transfer any sentence about finite sets to hyperfinite sets. Any questions so far? Okay. So now we're going to be talking about algebras, getting into the universal algebra side of the presentation and Dr. Insall's work. In universal algebra, we describe algebras as ordered pairs of a data set and a computational processes we call operations. Dr. Insall likes to think of them as computing systems when explaining them to people outside of universal algebra.
Danielle, I'm sorry to interrupt at this point. But it might be useful anyway. Where my mind is going is that because you're now, it seems like you're starting a new topic. Obviously, you're going to try to connect them. But I wonder, is the intent, very roughly speaking, to show how algebras can be understood in this broader, hyperfinite setting? And
absolutely, yes.
Utility in doing that. Okay.
We start here. This is just basic universal algebra. We introduce nonstandard methods down here, and then we use our notions of hyperfiniteness quickly once we get to extension monads specifically. But to make this very approachable, we're starting with the most basic level of it. So I hope those of you who understand this are not having your patience tested too much. So star transferring algebras, because of our mention of finiteness, depends on, of course, on whether A or O itself has finitely many members. Because the star of some algebra A is going to be the ordered pair of the star of each of its components. So if you have infinitely many data points, you're going to get more in here. If you have infinitely many computational processes, which Dr. Insall did not allow for in his original work, you get more computational processes. And that is often difficult to work with because that means you'll get new properties and new sentences that are true in the internal setting.
Can I clarify for purposes, because I interrupted you before. I think you might have said more, but in any case, for people who don't know this setting for an algebra, essentially O, I'm asking actually, I don't know for a fact, but I think that O is some sort of essentially endomorphism of arbitrariety on A, or some such thing, like, so that I'm trying to make sense of star O essentially,
Okay.
right?
So for example, we can talk about star O later. Let's start with a more basic example. Let's start with some group G. And let's say that G is, let's do the additive group of integers. So we're going to have the underlying set be our integers. And then we get an indexed collection of operations, including nullary operations that represent identity elements or other such fixed elements used in the equations that define the algebra. So for example, we're looking at additive group. So we've got our 0 element, we've got our additive inverse, and we've got our addition. Oh, whoops. And I believe that's everything in an additive group. Yep. And you can use this to describe any algebra as long as for each of these operations, they are compatible with every possible n-ary combination of elements from here. Or I guess, yeah, combination might not be the right word, but every n-ary subset of this. Okay, so that's what we call closure. And since this is a nullary, it technically doesn't require any inputs. But star O is when you have something complicated, like, say, instead of just our typical addition, or maybe we could do something. It's often hard to find good examples of algebras with infinitely many operations that are all sort of unique or distinct in some way. But we could look at something like 0, additive inverse, addition of 2 elements, addition of 3 elements, addition of 4 elements, etc. In the non-standard setting, you're going to get, in addition to the non-standard integers, which behave much like we talked about with the natural numbers, except it goes both directions. You're also going to get, might need to erase some of this because it's you're going to get a 0, and technically this is star 0, and this would be star additive inverse. And then you get star of plus 2. Sometimes we drop the star when it's clear what we're talking about. But you get more than just addition corresponding to every natural number greater than or equal to 2. You also get plus of mu many elements and mu plus 1 many elements, etc. The same way we talked about the natural numbers. You're going to get additional operations. And this is a fairly boring example because it's just iterated binary operations, but hopefully that demonstrates the sort of, oh, whoops, sorry.
Right. I was going to say, presumably it could also involve operations on multi-type objects, like, you know, sets of different levels and so on.
Mm-hmm. Though that would require your underlying data set and your operations to be compatible with that. So,
well, then, no, that's what I mean, right? Like, presumably, I was talking still before you take the star, I was talking about understanding the structure of O. For people unfamiliar with this way of describing what an algebra is, what is the, you know, the set of operations? It could, you know, it could be the kind of thing that is much more involved than just a regular addition.
Of course, yeah.
Okay.
Just starting with simple examples.
Sure.
But yeah, you can define algebras or underlying sets and operations in all sorts of ways. Though in our examples, we're always going to look at algebras where the data set is composed of atoms to make it easier on us. Because you can always just map the algebra underlying set into atoms to get an equivalent structure, homomorphic structure, or isomorphic structure, sorry. Any other questions? So now we have another non-standard methods, sort of very useful tool, but this is just describing what we use to get to there. So a relation between two sets, say A and B, is concurrent given any finite subset of A. For every finite subset of A, you can find a single B such that it is related to every one of those elements, also called covering them. Any questions about that? Okay.
Yes. Can you wait? No, sorry. I'm sorry. I was trying to think how to articulate it better. So when you said covering, right? I was thinking of, so is this a property of the two sets or of a mapping between them?
Well, the relation, it's a property of the relation, but the relation only
relation.
exists in the context of the two sets. Because we
Right,
view relations as
of course
collections of ordered pairs. So
right. So that this relation between them has this property, and for that matter, is it a directional property? In other words, or is it bidirectional?
I mean, it's directional in the sense that we only define it in one direction, but then you could just
Prove
flip
that
them. You could just define R prime as B R prime A if and only if A R B.
Okay.
And then you'd get the opposite direction could be concurrent or not.
Right. So essentially you can start in the way that you have it written. For every element of B, there's a collection of elements in A that cover it, essentially.
That's not quite true, though.
No, and you didn't say it that way. And so I was hoping that you'd say that's not it. You said it the other way. You started with the substance of A.
No, it would still have to be a for all elements of A.
Yeah.
Or for all finite subsets of A.
So so now the correct way, I'm attempting. Previously I said that motivated from the picture, but knowing probably it was wrong. Here I'm going to try now to be correct, but I don't have a lot of confidence that it is correct either.
Oh, okay.
So for all subsets of A, there exists an element in B that is covered by them. But I'm not sure by like all of them. I mean, it doesn't like, or what? I'm not sure. I mean, it seems
yeah,
like
the other direction isn't as nice. So I guess,
yeah,
in the sense bidirectional, it's not true that if A R B is concurrent, that B R A would be concurrent. basically, or BR prime A would be concurrent. So you could define a relation to prove concurrency one way or the other, but it's not guaranteed that if you've got it working this way, that you can
One
get
way
it
will
working
work the
this
other.
way.
So can you say it one more time the correct way so I can get that
Okay.
down? I was writing it
So
down.
for all A, or sorry, for all F in the finite subsets of A, there exists some B in B, such that A in F implies A R B.
I got you. Okay.
That's it in the most mathematically logical terminology. Any other questions? Okay. So containment, this is a fairly boring example, but we'll spice it up a tiny bit later. Oops. A relation on X to X is an example of one that's concurrent is containment. If you've got a finite collection of the powers of elements of the power set of X, then you can find a single member of the power set of X that contains it. Their union would be the most simple example. You could also find concurrency on the natural numbers by using greater than, or I guess less than. If you've got a finite collection of natural numbers, you can always find something that's bigger than all of them. And so the concurrency principle then uses this in a pretty powerful way. When you've got a concurrent relation between A and B, so R is concurrent in this case, then you've got that there exists some B, or I guess beta might be better, in star B, such that every element of A is covered by beta. When you look at the star R, of course, because otherwise you wouldn't be able to compare them. So in effect, what you're doing is treating A as a finite set in the non-standard setting. Any questions before I go back and show sort of an example? Okay. So if we change this relation a little bit, and we don't look at just all subsets, we look at only the finite subsets. So we're looking between right? You can agree that this is concurrent. Given any finite collection of finite subsets, you can find a bigger finite subset that contains all of them. Correct? Okay. Then in the non-standard setting, that means there exists a hyperfinite. A hyperfinite subset, which we can call H, such that every element of the finite subsets of X is contained in H, which really just tells us that X is contained in H, right?
Right, but by itself, that seems not that deep, only because H is supposed to be much bigger in any case, right?
But it acts like it's finite.
That's okay. Okay.
That's where it comes in. You can find a hyperfinite set that contains any set in the standard space. And that will be useful for some of our other things later, if we can get to them. Okay, does that make sense? Any questions? Okay. And then there are a couple of properties of algebras, or I guess relations between algebras that we talk about. So restrictions and extensions refer to altering our data set. Whoops, sorry. I forgot to set it to draw. If you've
Can I
got
just-
A,
Sorry, 1 second, Danielle. I was just taking notes on what you said before. Let me just rephrase it to say why I think it's important, which is not obvious. So, in the previous setting, in the example that you were showing, essentially you're saying that this extension principle, or this concurrency principle rather, essentially can show that there exists a hyperfinite set that contains all the finite subsets.
yes, which means that it contains the whole set.
Which is non-trivial in some sense, at least, at some level of understanding for me, because, the set that would contain all the subsets, would be non-standard, but not necessarily hyperfinite. In other words, it can't act as, a finite set in this, in the extended, in the star, universe, whereas now you're saying it can, in fact, so that, that's the strength of the statement relies on the fact that in this star setting, the set of all subsets of the original thing can be considered finite, even though, obviously, in the original setting, it was the biggest thing ever, right? So it's certainly infinite.
It's interesting how quickly you can shrink stuff down relative. But yeah, it's
the other comment I wanted to make, is more procedural, just for your pacing. I think maybe we should have another 10 minutes or so. So plan ahead, because I know some of it had to do with the fact that we started a little later, but just plan ahead. Yeah.
I mean, I can stop pretty much anywhere. It's not like I will die if I don't get to the theorems themselves or anything. At least I hope there's not a sniper trained on me right now.
Oh, and remember, you have to show us the reality of your background at some point. I think that
yeah,
is.
of course.
Yeah.
So we'll talk about some quick properties of algebras, given that A is contained in B. If you've got algebras AO and BO, and assuming that they're both closed, as we discussed, so every possible correctly sized collection of A can go into any operation in O and return another operation to return another element in A. Same for B. Then we have that this algebra is a restriction of the one on the right. So A is a restriction of B, and B is an extension of A. Basically adding or removing data points. Similar concept also works for reducts and expansions, except instead of the underlying set, it's the operations. If this is the case, then A1 equals A01, A2 equals A02. If we have this, then this is a reduct. A1 is a reduct of A2, and A2 is an expansion of A1. A retract of an algebra, so if you've got a large algebra B and a smaller algebra A inside of it, A is a retract of B if you can collapse it onto A, collapse B onto A, while completely preserving the behavior inside of A. So, excuse me, basically there's a homomorphism that is the identity on A. Okay. And I believe now we can get to direct sums, which in our case are going to be coproducts. We're looking at category theoretically and using the historical notion of direct sum. So when you've got a collection of summands, such as like A1, A2, A3, etc., and you want to take their direct sum, this will be the structure such that if all of these are morphically mapped into a single structure of the same kind, which we can call B, you can also always go through the direct sum and then into B, and you'll always get the same result, which is demonstrated on the next slide a little bit, but using commutative diagrams specifically. So this is one of the summands. If you have that one of these exists for the same B for every summand, then you can find that this phi exists up here. Any questions about that? Okay.
Are we? I'm always late when you ask that, and you wait patiently, and then I'm taking too long. But I'm wondering if is this something that we can extend? You made me think of hyper, like star n, for example, right? Like if this is traditionally we have this as a finite set of summands, or maybe even a sort of countable one. But are we about to extend this now?
We've also worked in uncountable summand or uncountably many summands. So
Okay.
we have looked into extensions and extension monads of direct sums, but that's a ways down the road, and I don't think we're going to get there in 10 minutes. So
No worries.
But first, let's actually get to the titular extension monads, and at least we can potentially finish with that. Or get to a theorem, maybe. So this is specifically most useful when determining the properties of algebras that are local. So related to either a finite set or a finitely generated subalgebra. We construct the extension monad by looking at the original algebra in the context of the internal algebras that are bigger than it and shrink wrapping onto it by taking repeated intersections of every internal algebra bigger than it. This is most of the time, unless you have a very boring algebra, external. Yeah, I think there's only one possible case where it's internal, and that's when it's finitely generated, but I don't think we'll get to that too much. Are there any questions about this or anything that you want me to explain a little more before we get into potentially a theorem about this? Okay. I don't think I'm going to have time to go over like the proof sketches that I had worked up,
Could you define the subreduct again? I think you did define it.
Oh,
but
yes,
I
sorry, you're
forgot
right.
it.
My bad. Yeah, so a subreduct is A is a subreduct of B. If and only if A is a subalgebra of some reduct of B. So it is both a subalgebra, so it is a subalgebra of a reduct, and we simplify that to subreduct. But yes, sorry, you are right. And this is the result of having potentially infinitely many operations. We need to remove the extra ones. Otherwise, the two algebras aren't directly comparable because they have different operation lists. So we're going to be using subreduct a lot. So thank you for pointing that out. So there are several different ways of defining extension monads or equivalent formulations of them. We don't have to look at only internal algebras, internal algebras, such that A is a subreduct. We can also just look at hyperfinitely generated ones. We can look at the algebra generated by the union of the finitely generated algebras, such that the generator sets are subsets of the original underlying set. And we can also look at the union of the hyperfinitely generated subalgebras of A hat. And I will skip these. Oh,
In
do
the
you have a
last,
question?
yeah, well, yeah, I was just wondering, in the last statement, there seems to be a kind of recursive call to A star. I mean, A hat, you know?
It is a little recursive.
Yeah.
All of these are,
Intention.
yeah. That's fine in this case because this isn't how we're defining it. This is just equivalent.
A
This is just
property of it.
equal. So
Yeah. Okay.
we're basically saying we don't get anything extra by doing this.
Exactly. Okay, good. Okay.
So yeah, that's fine. And I'll skip these slides unless we somehow magically have more time. There are a few examples of extension monads. I think some of the more basic ones that are still somewhat interesting are groups under multiplication and addition of the rationals, well, without zero for multiplication. For multiplication, the rationals without zero, you get the extension monad being the subalgebra generated by internal iterations, specifically hyperfinitely many iterations. So you can get something like 2 to the mu, or 2 times 3 to the, or 2 times 3 times 5 times all the way up to some hyperfinite number of iterations, but you can't get something that is like, for example, some non-standard infinite prime.
So you mean you can get numbers that are non-standard or hyper finite number of products of finite numbers, but not an external
an internal prime that's infinitely large.
Yeah, right. Yeah.
Yeah. The extension monad of the rationals as a group under addition is the group whose underlying set is the collection of fractions, such that every non-standard natural number can be a numerator, but the denominators need to be able to be expressed without using any primes, any infinite primes. Because addition and multiplication, it's not quite as nice to like describe it, but it ends up being pretty useful in that a lot of related things have very similar extension monads. And you can read the paper for more on that and for more details on this.
So again, the denominator can not be an infinite or hyper, an infinite
prime,
yeah. But it can be a hyper finite product of finite primes.
Of course. Or a hyperfinite, or yeah.
You know what I'm saying? Like an infinite.
Yeah, I see what you're saying. Yeah.
Like a mu product. Okay.
Yeah, and you're not going, when you get something like the 2 times 3 times 5, etc., you're only going to get the natural numbers multiplied together, because for any other number you could kick it out through the intersections, and thus you're going to get, what am I saying? You're going to get that this is external, and that this will also be these extension monads, which we call hats. These are all going to be external in these cases. So there's more examples, but let's get to the theorem that I included for a sort of basic utility of extension monads, and then we can finish up. Okay. An algebra is locally finite if and only if the extension monad of A, so A hat, when you remove the excess operations, which we denote by restricting it to O, our original operation set, just gets us our original algebra again. So basically, we have an equivalent equation that tells us if it's locally finite. And that's the most basic example of the utility of extension monads, because local finiteness is possibly the most basic local property. Any questions about that?
Yeah, I'd like to understand. So the utility, if I understand this correctly, the utility of this, big extension essentially
Mhm.
is that there's a property of algebras that has nothing to do with the extension that we're very interested in, namely whether it's locally finite or not. And and that it, in some sense, the implication is that if we extend this notion, right, if we look at this extension monad, which is a much bigger object, and then just restrict it to the original set of operations, we can test whether the original algebra is locally finite, which is something we
Yes.
care about in this larger setting more easily, essentially. More
Because it's
directly.
simply an equation.
It's simply an equation, exactly. It's simply an equation. Okay.
So that's the most basic form of utility, I would say in this case. But local finiteness is of interest to many people, so.
Well, thank you very much, Danielle, for getting even here and just basically the hour mark. This is really nice.
Well, thank you.
Thank you. Let's first of all thank the speaker. Let's see how we do that here. Thank you very much. I wonder if there are any other questions. I know we've been interrupting you and asking questions throughout, but if there are any questions by anybody in the audience, any context here to add. Maybe one thing that I will inquire into is where does this fit in this type of work? Where does it fit in sort of mathematics more broadly? Who generally is interested in these or uses these types of objects and results?
I mean, Dr. Insall cares, which is most important to me as a student. But I think I have attended some talks. Maybe one of them was at the AMS meeting or something that was somewhat related to this. Or at least I brought something related to this. I don't know.
I mean, to be more here's my suggestion. I don't know at all if this is true, but it seems to me that this, for example, if we see it from the non-standard analysis perspective, might be useful in understanding better kind of questions having to do with the continuum, like questions related to differentials or other kind of in probability theory or something like that. I know Irfan has probably some experience with that, but
yeah, this non-standard stuff is a good way of constructing infinitesimals and infinite natural numbers. So we've already discussed some of that.
Yeah, well, historically, non-standard analysis was partly motivated by infinitesimals. I think the applications in algebra started happening very soon after Robinson discovered non-standard analysis, and I think Robinson himself was maybe the first person to start applying in algebra. Then there are some more people working in algebra early on in the 70s and 80s. There was someone at Urbana-Champaign who worked with non-standard analysis in algebra. I'm forgetting his name at the moment. There are people who use, in general, they use ultra product methods. So I think the word ultra product was not mentioned today, but a lot of the times these non-standard extensions are constructed using this tool called ultra products, and ultra products are, I think I know some people in algebra who technically use non-standard analysis, but they call it ultra products.
Yeah, you can get more details on ultra products, both through my paper and also through what I source to the basics of non-standard methods. But yes, I did purposefully skip over ultra products because they are very technical. But yes, if you want more details, the archived paper should have some more. Thank you for bringing that up.
And in the context, since the ultra products were mentioned now, and you mentioned Wash's theorem earlier and so on, another area of, I don't know if it's proper to call it application, or where these notions might arise, that I've seen them, and I wonder, how it all fits together is logic, right? Extensions of logic, like logical theories, model theories. And I mean, while we were talking here about algebras, and in the traditional description of non-standard methods, you're talking about, numbers and sets and so on, but there's a relationship to theories of logic, essentially. Right? I mean, can you tell us a little bit about that, or do you know any connections with that? I'm thinking this could be, I mean, logic can be thought of as an algebra, right? Like as a Boolean algebra or other kinds of extended.
Oh yeah, Boolean algebras are.
Yeah.
Well, they can be described as algebras, and thus they are covered by a lot of what we talked about today. I do believe I go over some talk about the equivalence in our discussions about satisfies and star satisfies as being equivalent notions when you look at specifically standard sentences and standard structures. So that's also a little bit detailed in the paper, but this all, especially like stuff like the transfer principle, where specifically that is acting upon logical sentences. It's a lot to do with logic. I don't know how much I've worked on like too much of foundationally like new or different logic, though.
Yeah, I know that if Matt were here, he would say, I think, some things, because he has told me separately that he's been reading up on these kind of how do you call them, non-institutional logic, sort of basically within model theory, ways of describing alternate logics with essentially from scratch, without any like in this way, where you start with a nondescript object and then build structures from scratch, basically in a bootstrapped way. So yeah, that's I think a fascinating connection. Some of this also, I think, if I understand the history correctly, and maybe Irfan, you know better, but at the time when Robinson and others were working on sort of the foundations of this, there were also, well, I mean, Wash was a logician, and also others like Cohen and so on were very keen on these sort of sort of hyper finite, hyper real models as essentially models of logic, in the same way that the traditional set theory was used as a model for Boolean logic, right? Like these bigger sets, or the towers of infinite sets, essentially could be used as models of these extended logical objects. I mean, are you familiar with that literature, Irfan or Danielle, or anything like that?
What in that literature are you looking for?
No, I'm just thinking of in a sort of epistemological almost way, like the relationship between the logicians interested in this space and then the sort of the set theorists or sort of people who are just doing non-standard analysis for some other purpose, or algebraists for this matter, who might have, like, if there's any kind of interaction between them, or mapping. It seems like some of the same theorems are being used, even though they may have been developed for a different purpose.
Yeah, so it uses theorems from logic. Like essentially, Washer's theorem is a theorem in logic that you have a structure, and then you take a ultra product of that structure with itself, and then you prove that the original structure can be thought of as being embedded in a what they call it, an elementary embedding inside the larger ultra product. So originally tools from logic were used. I think the ultra product was not the first construction. Robinson's construction was using just compactness theorem in logic. So he didn't actually give an object precisely, which was the non-standard universe, but I think it was, let me think, I'm forgetting his name. There was someone, Luxemburg, or I don't know how to pronounce his name. after looking at Robinson's work, he came up with the idea that what he is doing using compactness theorem is essentially just the ultra product idea, and so the ultra product can make it a bit more precise in terms of seeing what we are working with. And so I think that became the more mainstream way of doing non-standard analysis using ultra products. Often when we do it, we don't actually refer to any ultra products. Many people who work, like when I work with non-standard analysis, I don't actually refer to any ultra product, but maybe whatever non-standard universe I have been working with, maybe one way to construct them would be using ultra products. But beyond that, logicians themselves, I think, are interested in ultra products for its own sake, and are interested in non-standard models of things also for their own sake. And my understanding is that a lot of logicians fully understand everything in non-standard analysis. They just don't work in it the same way I would say I work in it. They just understand it and they work in logic, and in logic, non-standard models just appear here and there. But for me, I don't work in logic. And so for me, non-standard analysis is more of a way to do mathematics itself, because usually mathematics is done with the standard framework. So I'm still supposed to prove standard results, but the ability to use the non-standard extension of a standard structure and then trying to prove things there and then getting it back to the standard universe still helps someone like me and other people who use non-standard analysis for its applications to mathematics to prove new standard mathematical results. So that's how I think a lot of the few people who do non-standard analysis these days, they work on applications in standard mathematics, and I don't think they interact too much with the logic side of it unless they are a logician who are also working on other types of logic topics.
I'm fascinated. I think at some future event we might invite a logician to give us their perspective on this, and that it seems like a plausible bridge here that might, not have been as exploited as it could. But in the meantime, I'd love to know, Danielle, as a final question here, where are you planning to take this? What are your plans going forward? I mean, I realize you just finished your thesis, so how does this fit within your?
I'm not done my thesis yet.
Oh,
Sorry.
you're in the middle of it. Okay.
Mhm.
So where is this taking you? How does this fit with your larger plans in math? You're not sure?
I don't know. Honestly,
Okay.
I am unsure of my future.
It's a fascinating time for you. I remember for myself, it's sort of like both simultaneously like bringing everything together that I've been learning, at the time, into a coherent whole, and at the same time opening up so many possibilities. So it's kind of a funnel point in history for you. So I look forward to hearing where this takes you and staying in touch. Thank you very much again for taking the time to share with us these insights.
Thank you for
would you
having
mind
me.
telling us about just showing again that the reality of your background, because I think this does
Okay.
deserve to be shown. There you go. It actually is real. It's not a background. It's hyper real.
My mom has interest in French architecture, so they designed the main room to look like a Parisian street, I believe.
Awesome. Thank you. Look at that. I love it.
Unbelievable. Thank you, Danielle.
Oh,
Thank you
you.
very much. Yeah.
Thank you.
Bye.
Yeah. Bye-bye. Thank you, everyone.
Bye. Thanks, everybody.
I just ended the YouTube live stream.
Okay. Excellent.
you.
Thanks, everyone. Bye-bye.
Everybody.
Bye-bye.